started. So I'm Paul Cox. I don't work for Arduino or MathWorks. I worked for MathWorks in 2017 and before when I worked on this project with Arduino. I've been working with MathWorks for 6 years at the time. The kit came out in 2018, so it took us about 9 months to make this. I've been going to maker fairs for MathWorks for I think about 3 years. I'd go to the Rome one because I was based out of Paris. At the time, MathWorks had just started marketing a home edition, or like a non-commercial license for hackers out there to be able to use MATLAB. People that aren't students, people that are professors that aren't and don't have it commercially. They wanted hobbyists to be able to have it. So going to the fair was a good way to get the word out that it was there. It's a couple $100. You can buy it if you're a fan of MATLAB. It's an option. So the idea was, that we've been going for a while, was to create kind of a college level course, not really a full course with a syllabus, but content at the college level that would just basically give you an idea of how to use MATLAB and Simulink for a simple mechatronic project. Arduino has always been very big in maker community, and at the time wanted to get more in the education space, so it was a natural meeting of the minds, and us wanting to get a hobbyist, then wanting to get an education. So we decided to collaborate and develop this content, and I was the person that developed the ideas, the concepts for the actual projects that I'll detail in the rest of the presentation. So I got about 20 slides just to kind of show you what's in the kit, what we did to design it, what we ended up with. David Quartieles, a Spanish guy that co-founded Arduino, runs an office in Sweden, southern Sweden, kind of the suburbs of Copenhagen, Malmö. And I worked principally with him to kind of get the initial concepts figured out, and then Tugru, really cool Turkish guy who works in Malmö, or did at the time, would take my designs and kind of redo them for things that they could actually produce at scale. And there were a couple of other people on their side that helped for electrical design, firmware, and I did a bunch of that too. And we got some, like I was mentioning, a lot of the MATLAB content, Simulink, it's all kind of done by others. Once we had a working kit, then the content people could kind of unroll all the pedagogical content. And there's some really cool stuff there, which I won't show today because of time, but lots of really good ways to learn motor control and all these different things that I hope to, at a high level, detail today. The kit's on a Rev 2 now. I forget when I came out, maybe last year. Just make it a little simpler, maybe some less cost. And the whole idea is you use these parts to make 3 different robots. You can't build them simultaneously because they share kind of the main components. So you have to tear one down and build the next one. And I'll go through each one of these here in a second. And it all uses this MATLAB license. You get a free trial with the kit when you buy it. It might be time limited. I can't remember exactly the details. It might be perpetual. It's all fairly relatively low cost. With the kit, I think you can get it at DigiKey and Mauser and basically all the distributors for like $279, and it includes the license. This is the price if you were just going to buy the license by itself on the website. The main components, this is what I'm mostly proud of. This is an off-the-shelf Maker 1000, so a little microcontroller with Wi-Fi. It was kind of imposed on us. We needed to use this. At the time, I think it was relatively new. It plugs into this daughter board. This you can buy without having to buy the whole kit. I'm a big fan of this, partially because I helped design it. It's got, when I set out to develop this kit, I really want it to be more than just a little random robot that can move around randomly. I really want it to be, having coders for precise feedback. I want to be able to measure current, so I know my torque. This has all of that functionality, even a LiPo charger and lots of servo drives. And I use mostly these Palum. Most of this stuff you could kludge together from Palum boards. This is a nice way to have it all kind of together. And the schematics are available on their website, like with everything else. So again, if you wanted this to be on with a cutie pie or something else, you could put your own little motherboard or other microcontroller on there. This has its own microcontroller. The main thing I wanted to do is make all these interrupts coming in from the encoders not something you have to handle on this guy. This guy can handle all of that, and just so the high frequency position control stuff can be done here. There's libraries provided by Arduino. If you want to do it yourself, you can do that too. You got the pins and so on. So the rest of the presentation is kind of the 3 robots and the process I used to initially to just prototype the idea and then kind of mature it and get it to a way I can give it to Arduino and then work with them to transition and make sure it works. Here you can see one of the nice things about that motor carrier board is you can plug in your debugger and you can do some real debugging on that little SAMD 811 that's on the carrier board. So very useful little board. Initially, that came towards the end of the project that we had a mature version of this board. So until we had that, I was kludging together other things, like I said, Polo boards, mostly. And then as the hardware matured, moved to the real stuff. So those are the 3 projects. We have a little whiteboard robot. You can see there's 2 whiteboard pins. There's 2 motors, little spools, and so the idea is you hook your spools to the corner of your whiteboard, hang it, and then it moves around, drops the little pins down and up, and is able to draw things. A self-balancing motorcycle. So you got this inertial wheel, a lot like that little nanosat that you saw out there, a little inertial wheel to try to generate a torque, keep the motorcycle upright, whether it's moving forward or not. Those might be the more complex of the 3, and then a little differential drive, little rover bot with a little lifting mechanism to lift the little crates. So you can imagine little games. I don't know how much the content goes into like little games you could do with a lot of these, but that's what I had in mind initially. It's like, let's get a bunch of these, a bunch of students getting kits, put these together and figure out lots of challenges. All right, so the first robot was the whiteboard bot. I typically start with, not always, sometimes I start cutting plastic right away. In this particular case, I think I fired up OpenSCAD. You can see there's kind of one big disk. I think one of the motors is stuck to the disk, and the other one's free to rotate around the center point, which is not obvious from here. But so as the robot moves around, the angles change. You're able to rotate around that center point, keep everything kind of precise. You got pulleys on the edges, and the fixed point string goes around to the pulley. And then the idea was to have multiple pins, pick your color, one servo select, and then one servo to put the pen down or pen up. So here's the first prototype. It's foam core board or PVC sign board or something like that. Something I can just kind of cut with a razor knife. With everything just kind of double stick taped. And it was just to kind of establish feasibility with a quick little video of, this is even before I even hooked up the encoders, really just kind of moving motors, making sure it stays hugging the whiteboard, it's not flopping around, and just making sure, just initial concept validation, I'd say. I think it pops the pen up at the end. Those were like little Delrin things I machined and just kind of happened to fit the MathWorks whiteboard pins exactly with interference fit. Next slide, please. Yeah. And then once I provided the generic look of the thing, Tugrul and Magma, changed the design to use laser cut or cut ABS plastic sheets. I think in there's this kind of the center section where the hardware is mounted, and this one that board wasn't ready yet, so it's just there, not actually doing anything. This board still drives it, but the center section has the pins and rotates relative to these two that are rotate around this axis here, and the motors just live on the edge. So relatively straightforward and simple. The whole idea is to provide a very simple robot that then on the algorithm side, the kit teaches like import an image, create vectors, so it teaches all the different steps of that, right, to a college student or a motivated person to, how would you digitize an image, how would you create vectors, and how do you, and at that point you have like G code, and you just kind of send the position information to the robot, and that part's really trivial. The second robot is that little rover. The end product looks quite a bit different than the initial. This is an initial, again, foam model that I just kind of cut up without really overthinking things. I really wanted it to be able to operate like the skid steer, right? What do they call those? The loaders, the skid steer loaders or something like that. And the Bobcats, and John Deere makes them. There's really, one guy sits in there and can move the forks up and down. They usually have a really nice big ratio of being able to lift something quite high for the size. I'm going to try to achieve that. The end result is kind of not that great as far as that's concerned, but then again, it's not really a needed feature. The second prototype designed with 3D printed parts, so a little bit more refined. Kind of the same form factor. Initially wanted to be able to remove the forks and lodge the lift mechanism so that it could be an inverted pendulum robot as well. That wasn't an idea that was retained, which makes sense. We already have an inverted pendulum in the motorcycle, which I'll talk about here in a minute. Same motors with the encoders, so you can do some nice precision navigation. A little RC servo motor to lift the mechanism, and just a free wheel for it to rotate on. This was when I first got some of the PIDs loops running on that motor carrier board, just giving it random set points for each wheel, how many millimeters or ticks to move forward and backwards. Just kind of playing around, making sure that it could move and not fall over. And that's the final prototype I designed, and kind of the end result that you'll get in the kit. Always this kind of laser cut ABS. The same wheels that are used in the motorcycle are used here instead of the little ones, and the lifting mechanism. It's been a little bit simplified. I think this was supposed to be a computer vision target. The kit, at least version 1, had a little USB webcam that was provided, and the idea is you set your laptop in front of your robot, and you can figure out where it is in the room, and orientation, position, and command it around, and maybe have multiple. I'm not sure if Ref 2 still does that. This is the last project. This is the motorcycle. This is kind of the intermediate prototypes. I'll start with the beginning, chronological. So initially I wanted to do kind of what these guys did. Apparently they built what they call like impulse simulator or something like that for the CubeSat that's on the table. Because I don't know if you've noticed, inside it there's a big giant coil, and then there's also a reaction wheel in there. This is standard satellite stuff. They use the reaction wheels to create counter forces to change the attitude of the aircraft. Those are great, except that once you've spun them up to maximum velocity, they're saturated. You can't generate torque in that direction anymore. What do? Well, you use the Earth's magnetic field, which is very weak, but it's there. So with the coil, you can interact with that magnetic field, generate a torque, and start to slow down your reaction wheel. This is a master's level class I took, where they had a lab set up with these units. This is like a single axis. I'll just run it so you can kind of see the idea. It's a satellite, but in a single axis. So you just have like this board on a bearing, and you put a motor anywhere on that board, and you'll generate a torque if you start spinning the wooden disc attached to the motor. So it's a great way to do PID position control on one axis in a little bit novel way, and it's something that you can kind of think about space, and it makes it motivating for students, right? So I wanted to do this, pitched it to Arduino, and they're like, that's way too nerdy. Like, we want this to be like, you know, cars and trucks and airplanes and like something, you know, really motivating. So I'm like, all right, well, let's do the inverted pendulum, but in like motorcycle way, so that's cool. And then we'll still do a reaction wheel to control it. So kind of the same dynamics a little bit, and the inverted pendulum. This is an early open scat design, showing we drive the motor to make the motorcycle go forward and backwards. I had a little suspension. I don't think that in the end there's suspension, but that could probably be added for the final. A little inertial wheel with the motor. You control the speed. You can measure the current, then you know the torque you're applying, so that's where that motor carrier board was really handy to have that current measurement. And then some servos. This one's for steering. This one ended up not being including. I wanted it to have a little self-deploying kickstand, so that instead of just falling over, if you saturate the wheel, you could pop out the kickstand and then ride it back up. That didn't make it either, unfortunately. You could leave it to your advanced students to add that. For extra credit. This was the very first prototype. It was literally cutting board, poster board with an X-Acto knife, and throwing some dowel rods and some balsa on there, and just to kind of validate the concept. I don't think I did any balancing at this stage. It was more just to try to see. We had a little IMU here, so I could just make sure I had all the drivers and everything I needed to move forward. Second foam prototype. With a little bit of suspension this time. Still using the Maker 1000 with kind of hand-assembled Pololu modules. And then this was a prototype made where I wanted to start actually balancing the thing. So I wanted to, obviously once you have your control loops really dialed and you know exactly what you're doing, you don't need that much current, you don't need that much torque to stay above the balance point. So I over-engineered this one just to make sure I had plenty of current driving capabilities. I wanted to be able to really punch it with like 3 amps if I needed to, since this is early stages. So I used a big driver board from Pololu, Arduino Duo, so I wouldn't have an extremely tiny microcontroller. This is probably the IMU, which I try to keep as low, keep the axis of rotation as close to the fulcrum as possible. There's a version where I was finally able to add my dream feature, which is the little deployable, which I was able to do with a single servo. And deploy my little training wheels. Note to self: don't do what I did here. To add mass in my reaction wheel, I thought it'd be really smart to just use the coins I had on my desk. So I 3D printed this thing with some recesses to put the coins in there. I think I even put a little hot glue, because I didn't want them flinging out. And guess what happened? when I saturated the wheel and the thing's flying at, however many 10,000 RPMs, one of the coins was flying out of there.
Did you find it?
So, needless to say, that feature did not make it to the final kit.
Was your machining precise enough to actually get good balance, or was it getting some issues with being slightly off balance with the extra mass in there?
Yeah, I think probably the wobble. Yeah, it definitely wasn't precision. This is just a crappy 3D printer. And the axis was just an interference fit, and it definitely wobbled at high speed.
Yeah, a uniform density disk is going to do a lot better with that than.
Yeah. In the end, this is not the final result. It's a little cleaner than this. This is my Duo with the Pololu motor drive, but the plastics are starting to get really close to the end. In the end, they use 2 or 3 of these ABS discs to give the mass. And then we use a remote control airplane prop holder that's like collet based, so it's kind of self-centering, relatively precise. You can kind of see it better there on that one. It was a 3S battery in the day. Now they're shipping with that 1S cylindrical cell. I wanted punch. I wanted a lot of voltage, so I used 3S. They eventually figured out how to reduce that. And I think, just to say a few words about the control aspect. I initially developed all of this stabilization directly in the Arduino IDE. I'm a professional firmware developer and electrical engineer, so I typically don't use the Arduino IDE. I want breakpoints and things like that. But I thought, I'll give it a shot. Let's see how. And I basically just used the serial plotter to plot my PID terms and watch them, and I could tune my gains. Worked pretty good. And then once that was done, I re-implemented it in Simulink. For those that don't know, Simulink lives in MATLAB, and it's a graphical programming environment. It's more than just programming. You can actually do full system simulation. So the PID loop looks basically like this. You've got your KP, KI, KD, your gains essentially, kind of trivial. There's a little bit more funniness that has to happen for this to work, because you don't really know exactly where the center point is, and it might actually change with time as the battery moves around. So it's a little bit more than that. I call it a leaky integrator. So it's basically some little tweaking of the integrator that gets you kind of this self-centering capabilities. And then all the low-level drivers for sending the wanted motor torque to your power electronics in the Simulink world ends up just being a block, which behind is just equivalent to like analog write or something like that in Arduino world. And I think I have a little video of one of the very first stabilizations on my workbench. I'm trying to show like perturbation rejection. I'm banging on the thing, and you can see the wheels kind of sometimes moving in one direction, sometimes moving in the other. Sometimes I hit it a little too hard, and it tips over. I think at one point I pan over to that Arduino plotter. You can kind of see the different gains and sort of the terms growing and increasing. There's a little piece of tape to help you see. This was all, obviously, the motorcycle's not driving. I did have some tests. I don't think I put them in the presentation. I did go to my driveway and set it on its way, and then I started playing. I'm not sure if it made it in the content, but playing with, you can, obviously, when you're on a motorcycle or a bicycle, you can play with, moving your weight side to side. You can play with the angle to help you. You don't need an inertial wheel, obviously. If you had an inertial wheel on a bicycle or motorcycle, you could use that as an extra way to be able to the side. So I started playing with
steering, right? Because you would need an additional motor otherwise to control the front tire, or you could just let the motorcycle lean left or lean right to start to look big.
Sure. Yeah, I think these tires have a flat profile, so it might be harder. But yeah, you could put round ones and then just this one has a servo, so it will let you change the angle of the drive wheel, a little servo over here. But you could use both. It's an over-controlled system, which is always fun to play with. Control systems, right?
So do the student end users set, is part of the task for the student end users to set the PID parameters such that the motorcycle will balance, or is that just designed into, is that controller sort of pre-designed for them?
Yeah, the content, again, I don't have it to show you, but it's really kind of everything in MATLAB and Simulink, pedagogical content usually is like from first principles. So they'll teach you, the first thing they'll do is have you model the dynamics of the system. And then you'll introduce a controller, try to affect that dynamic, and then you move to actually doing it in the real world. And doing it on the motorcycle. So it's definitely fully open book.
Learning the PID system is a big part of the kit then.
Learning the dynamics and then learning PID,
Yeah.
and then implementing the PID. Yeah,
Cool.
Absolutely. Yeah, that was really the vision of the kit, is to really provide a full modeling perspective to getting the. It's not really. This is a kit of bots. This is a kit to learn everything that's involved with controlling a mechatronic system. Well, not all mechatronic systems, because there's a lot of them, but inverted pendulums and PID gets you 95 of the way where you need to be to do the basic things in life.
Yeah. I used MATLAB and Simulink in school for chemical engineering, and so we simulated chemical systems.
Yes.
but because I was not, we didn't do any robotics. At least I didn't.
Yeah. Well, the base Simulink, what's great about it is
Yeah.
really just differential equations.
Yeah.
You've got integrators, and once you've got integrators, you can do how many n-order differential equations. So it can be chemistry, it's any domain. There's no units. There's no mass or whatever. There's another platform that lives in Simulink called Simscape, and there you have like domains, and each domain has, if it's a mechanical domain, you'll have inertias. If it's an electrical domain, you always have your across and through variables essentially, and each domain has different units and for all those, but the principles rest the same because at the end of the day, it's all differential equations.
Yeah, if you have differential equations, you can model anything basically.
That's why we were targeting that college level, right? Because you're starting to learn calculus, and this gets you to use it, and in a practical way. You start with the mathematical, and then you move to the practical. Yeah.
How much do these different robots weigh? Like,
I've got a few prototypes. If you want to hold them, yeah. They're like 100 grams. Wow, a lot lighter than I expected. Yeah, it's just pass my junk around if you want. I brought some of the. It's a few years old now, so they've been suffering in some of my drawers. But yeah, if you're interested, come see them. Yeah, the whole kit is like this big. So you could have 20 of them on a shelf for your students. Any other questions? Yeah.
Yeah, if you were to do another iteration, or if you got any feedback, what you would do again?
Yeah. So I worked for MATLAB for 6 years, and at the end of that, they retained me as a consultant to finish this project. And then when I left, they just handled everything internally. So I've completely not been in the loop. So in terms of feedback, I would love to hear feedback because I'm totally out of the loop. So honestly, I wouldn't know how to mature it and how to improve it without getting more feedback. I'm sure I've got lots of ideas and other types of kits I want to build to improve this one. I've been too much in the dark to know.
I saw several times in a very early prototype was cut out of foam core, and I've often sort of I thought of like cardboard as like a great prototype.
Yeah.
I'm guessing like this.
The best is that because foam core, is pretty easy to crease. Like you just grab it and you start. I don't know if any of these are made out of it. There's almost nothing to it. The inside layer. It's like two pieces of thin cardstock, right, with a very light foam in the middle. So like only the crudest prototypes I would recommend that for. The next level up, which is really nice, is the PVC sign board, they call it, which is an expanded PVC. So you can still cut it with a razor, but like it takes a lot of force. And I think what it is, it's two sheets of very thin PVC with an expanded PVC in between them. So it's like much harder than a foam. Like, to compress it, you really have to like almost stand on it or put a chair on it to get that kind of. I really like that. It's almost like a easy to cut plywood.
And so then I feel like
You
different
can
from that
even
one.
tap it and screws in
I would say
there.
like probably your standard hardware would work with that.
Yeah.
I
You can tap the edges, which is really cool, right? Because a lot of things when you want to put two sheets together, you want to use a fastener, and this stuff will let you tap it from the edge.
Can you do some of the same things with one core, like using shelf hardware to like switch together in boxes or something like that? Or is that more like, I don't know how to do this and how to do this.
Yeah, that foam core board is pretty. It's basically cardboard. It's really easy to bend and doesn't hold the hole very well. Definitely can't put threads in it. A lot of people like to use acrylic. I think and then if you've got a laser cutter or water cutter or whatever, that gets you a long way. Or 3D print stuff.
You said it took 9 months to develop. How long did each process? Like ideation, like prototypes.
Yeah, I think I talked to David for a month or 6 weeks about what projects we wanted to include at the concept level, So that was just kind of discussion, sketches, and then I would disappear for 6 weeks to create one of the prototypes, and make sure it was feasible. And I felt kind of warm and fuzzy after prototype 1 or 2, like I showed. I would show it to them, and they could start noodling on how they would redesign it for ABS, while I started, for the next 6 weeks on the next robot. Some were more complex than others, so 6 weeks is an average figure, but yeah, kind of different phases like that. Yeah. Do you know one?
Yeah, I was just
Go ahead.
curious, like, how much of the curriculum, right, of your target students did you know about? Different schools have different things they emphasize and that kind of stuff. Is that just a little black box to you, or?
So when I worked at MathWorks, I was an application engineer and consultant engineer, and sometimes I was pulled in for trainings. So the whole idea of creating courses, while I'm not a professor by any means, creating your objectives up front. That on a hobby or just on a side project.
So that was
for
like
me.
that was personal knowledge that you really brought in.
Yeah. As part of MathWorks has a huge user base in the educational world. As an application engineer, I would visit a lot of them and see like what they did in the lab and how they did it and what they did, why. Granted, it was in France and they have a slightly different educational model there, but the fundamentals stay the same. And then the make community and seeing how people use that too. We tried to make it dual path, right? Like it would be self-learners. It's a home use license that we were promoting after all. So like, yes, we want to target the college classroom because we know MathWorks knew that they had the model there and they could sell thousands of these kits for Arduino. But at the same time, always have that self-learner at home that wants to learn control systems, and may not have a professor, and may not care about complete coursework. It just wants to like make these cool things work in an intelligible way.
Yeah. Cool systems are cool.
Thanks. Any other questions? If not, I think Nordic has a. I don't see them, so we can keep going until they show up, I guess. So yeah, thanks for listening. And if you want to hang out, feel free to stay and take a look.